introduction of NMR and μSR, and how one can apply these things in the solid state physics. Okay, so now the file has changed, right?
Yes, sir.
Okay, so I have constructed my talk is as follows. First, I would like to give you a brief history and development of the technique nuclear magnetic resonance. And after that, I will talk about where to locate NMR, because as we talk about condensed matter physics or solid state physics, where this NMR technique is actually located, this is important to share. After that, I will talk about, in general, the experimental conditions, or what are the experimental equipments you need, and how the whole experimental things works with the NMR. Followed by this, I will try to give you some application where actually this nuclear magnetic resonance technique one can apply in the field of magnetism and superconductivity, or in general in the context of strongly correlated electron systems. And after that, I would like to give you a very specific example what actually we have done out of our many research topics. One of the topics I would like to share to the those who are interested to do research in the field of condensed matter, in general magnetism and superconductivity. Okay, after that, I would like to talk about muon spin rotation, but an application, but I don't know how much time I'll get. Okay, so as far as history and major achievements through NMR is concerned, so around NMR has a long history now, yeah, already. So, you know, the previous century, around 1930, already the concept of electron spin was already available, yeah. So the people, the scientists around the world used to know that electron possesses magnetic moment, and that has been had been experimentally justified or verified by the Stern-Gerlach experiments. And idea was emerging that atomic nucleus have both spin and magnetic moment. And after that, you know, around 1940s, there was a devastating Second World War, and so therefore at that time the radio frequency technology was developed significantly, because people had to share their information from one place to another. So the radio frequency technology was significantly improved, and that actually all things helped. In 1946, Felix Bloch and Edward Parshall, both independently in different parts of the United States, observed this NMR signal from water and paraffin. And the discovery was so intense and so informative and so intense that in 1952 they were awarded by the Nobel Prize in Physics. Yeah. Even though the discovery at the outset, the NMR was a technique discovered by physicists, but later on it actually took also a lot of in the field of chemistry, biology, and in modern day actually you have also in the medical science. So in 1991, so Richard R. Ernst from Switzerland got the Nobel Prize in Chemistry for his contribution to the development of the methodology of high resolution nuclear magnetic resonance and NMR spectroscopy. And after that, this also another Nobel Prize in Chemistry, 2002, for the three-dimensional structure of biological macromolecules in solution. And the story didn't stop. In 2003, this Paul C. Lauterbur and Peter Mansfeld also won the Nobel Prize in Physiology or Medicine for the discoveries concerning magnetic resonance imaging. Even though they are calling it actually magnetic resonance imaging, but in reality, in our opinion, it has to be called nuclear magnetic resonance, because the resonance is actually taking place at the nucleus. Anyways, so there are 4 Nobel Prizes in the field of nuclear magnetic resonance in general now, directly related to the nuclear magnetic resonance technique. So the wishful thinking, some bright future is there still. Okay. So now let me talk about that. When you were talking about the in general solid state physics, the research in solid state physics, and the research in general in solid state physics can be disentangled into 3 parts. Usually I try to see it in this way. You try to measure first the physical properties of a solid state materials, And then you try to do some kind of measurements to understand these physical properties, and you vary the environment to really see what is happening with this different environment, like temperature, magnetic field, electric field, pressure, and most recently people are quite extensively using also the uniaxial strain and stress. So what are the physical properties you do? You measure structure, you measure conductivity. In this conductivity, you measure thermal conductivity, optical conductivity, and then electrical conductivity, and that tells you actually whether the system is insulator or semiconductor or semi-metal or metal or superconductor. Yeah, and then you do also get the information about the magnetism. So this paramagnetism or ferromagnetism, ferrimagnetism, helical magnetism, and also you do the plasticity and so and so. And to do that, and of course for that, you need to have a very good material development. So that means the material is a very important and essential part. Those who want to do the solid state physics research in general, or the material science research, or the condensed matter, most recently people usually call it condensed matter physics. Anyways, the measurements you want to do all these physical properties, the thermal resistance, electrical resistance, specific heat, magnetic susceptibility, luminous rate, acoustic absorption, nuclear magnetic resonance, and electron spin resonance, and then muon spin rotation, and so and so, and then neutron scattering and Morse-bus spectroscopy. So that means when you are going from this thermal resistance to your neutron scattering, your energy is actually increased. Yeah, so this is more or less when you are talking about the neutron scattering or neutron diffraction, you are talking about more or less the energy scales in the milli-electron volt. Yeah, but NMR is actually located in the energy scales of fraction of microelectron volt. That one should really know, because your frequency range, you are varying from 1 megahertz to 1000 megahertz around in this range. And then you make a kind of, as I already mentioned, that you vary the environment of the system, like temperature, low temperature you want to do, or high temperature you want to do. You can vary fields, now low field to the high field, wide ranges of field you can do, and also the electric field and the pressures and so on. So these are the more or less the framework of solid state physics in solid state physics research, and then you can pick up whatever you want to do and how you want to do and what you want to do. Okay. So let's go to the next part. Now, I already talked about, in general, the solid state physics. Now, if you really want to do some science, some research on in general the magnetism, so or in superconductivity, what you do basically, you put your magnetism and superconductivity in materials at the center, and then you do some kind of excitations in your system or the probed system, and that excitation, and also you vary the environment and you make a detection. This is the way actually your measurements of magnetism or measurements of the magnetism and superconductivity takes place. Okay. Let's go to the next slide. Here, I would like to tell you that what are the application range of NMR. So in the beginning, I told you that NMR has now extensively useful technique for different fields of science. So I actually try to tell you in 3 ways. So for example, you can use NMR in the field of physics and engineering, like magnetism and superconductivity, the structure of surfaces and interfaces, the phase separation, lattice dynamics, and in modern time NMR computer. And you can do extensive application of NMR in the medicine, and in the chemistry, the chemistry in biology, structural analysis of molecules, DNA analysis, the very widely field you can do NMR, and you can successfully apply your NMR technique. And as far as incredible physical tool is concerned for investigation of matter, there are diverse areas of application, starting from brains, bones, cells, to oil wells or Antarctic ice, and then many places you can do this diverse fields of application of NMR. Anyways, as a physicist, from our perspective, we are more interested in superconductor or quantum geometric phases or different kinds of magnetism and so and so. So can you hear me properly, and are you following everything?
Yes, sir, you are audible. You can
okay, but I'm visible also or not?
Yes, sir, we can audible.
Okay, that's great. Okay, so Now let's move to our next slides. There, I would like to tell you about this. In general, when you are talking about local probe techniques or the microscopic measurements, and how we actually differentiate with some kind of scattering techniques. So here I try to make a schematic presentation, schematics of three things like nuclear magnetic resonance, and then muon spin rotation, and the neutron scattering. So you know, this nuclear magnetic resonance and muon spin rotation are the two of the local probe techniques, yeah. And the neutron scattering is a scattering technique, and all of them has a different energy scales, yeah. So in nuclear magnetic resonance, you are essentially doing your nucleus is there, so that means you know where is your nucleus is located, yeah, and that nucleus is actually interacting with your surrounding electrons, yeah. But in muon, what you do, you muon produced by the accelerator, and that muon you are implanting at the interstitial site. So muon try to find the minimum potential energy of the lattice, and they try to sit there, yeah. So the shortcomings of muon is that you don't really know where your muon is actually sitting, yeah. But the positive effect of muon is that from the muon experiments, you really all the time, you need not to bother about the thermalization of your muon or the signal intensity and so and so. And on the other hand, the neutron scattering is more energetically higher in the range, and there you can produce, your neutron flux is coming and scattered by these atoms, and then get the information about your crystalline periodicity, crystal structure, or the magnetic structure in general. So in the bottom, I try to show you at the time window for different experiment. This is a very important picture. I actually like it very much because that gives you the information what kind of time window and what kind of time ranges actually you are probing when you are talking about the neutron scattering or the Mosbar or the MUSR or the magnetization. So you see, so your time window of NMR and ESR and MUSR is basically sitting in the range of fraction of microelectron volt. So that means, so 10 to the power minus 10 to the power 0 to 10 to the power minus 6 second in general, you can vary. Yeah, you can get the information for the time. So that means if somebody asks you that what time energy, what energy scales actually you can get the information about the NMR, then you have to tell that we can only do the very low energy scales experiments. I cannot give all the information if you really do this muon and also the NMR. So these are the restriction one could have when you are trying to do this nuclear magnetic resonance or the muon spin rotation experiments. Okay, so far so good. And you know, when you are doing this condensed matter, the solid state physics nuclear magnetic resonance, so this is actually the periodic table. So in this periodic table, we can see from a different nucleus are very, very useful for doing NMR, and in particular in the solid state materials. If these are the nucleus in the green zone, like proton, lithium, sodium, and then vanadium, niobium, zirconium, yttrium, in enriched iron, cobalt, copper, so like aluminum, silicon, phosphorus. So more or less, these are the nucleus are very good and very good NMR sensitive nucleus. So that means if these nucleus are actually present in your material, yeah, then you can tell, okay, it is more likely that you can get a very good NMR sensitive NMR signal out of it, and which is very important because all the nucleus you cannot do NMR. That's the shortcomings of NMR. So that means the getting signal is an issue. I'll slowly explain you why this is an issue and why this is so difficult for some of the nucleuses. Okay, so now let me tell you a little bit more about the fundamentals of basic principles of NMR and physics-wise how we can see it. I try to minimize as minimum as possible the equation because initially I heard that there will be the general audience, so therefore I try to optimize the minimum equation so that it would be more generally accepted talk. That's the idea. So therefore, but still there are some equation you have to bear with me. Okay, so you know that when you are talking about the nucleus. So nucleus is actually, you have a, if you have a spin 3/2, and then nucleus has a kind of degenerate energy levels. Yeah. So now you applied a static external magnetic field, and then what happens? The degeneracy of your nuclear energy levels is actually lifted. Yeah. And so then, for example, if you take a spin I 3/2 nucleus, and then you are getting a kind of population of like this. So your population is actually increasing with as you go from M 3/2, it decreases as you go from M 3/2 state to M minus 3/2 state. Now you know the Boltzmann distribution function is actually Pm proportional to exponential e to the power energy of the cavity. Now, the nuclear magnetization, when you make a simple calculation and you end up with a nuclear magnetization, which is actually proportional to your spin, and then magnetic field, and inversely proportional to your temperature. So the interesting aspects of nuclear magnetic resonance is that, and when you are talking about the electron magnetization or the electronic magnetization, this is actually 10 to the power 6 times smaller than the electronic magnetization. So that means that's the crucial part of NMR. So that's the reason it is called that NMR signal intensity is very, very weak. When you are talking about electron spin resonance, which is directly connected to the electron spins, so there the magnetization is much more stronger. It is at least 10 to the power 6 times stronger. So therefore, it is much more easier to get the signal intensity is much stronger. But NMR, your signal intensity, this is the reason that it's very, very weak. Okay. So now what you do, so you splitted your, by static external magnetic field, you splitted your degeneracy of the nuclear energy levels has been lifted. Now you apply a time dependent oscillatory perpendicular field to make to satisfy the resonance condition, and this is the resonance condition omega L equals to gamma B0. Okay. Now, for example, if you take a spin 3/2, so there are two ways you can satisfy this resonance condition. One is actually called the frequency sweep experiments, and the other one is called the field sweep experiments. So in general, those who are doing actually the chemistry, they are essentially doing the frequency sweep things. But those who are really dealing with a very broad line or the strong magnetic internal field is very stronger, there they have to use a kind of field sweep NMR. So therefore, there are two ways you can do is either the frequency sweep or the field sweep. So in both cases, when you are doing the frequency sweep, so that means you applied a static magnetic field, and that is the fixed static magnetic field, and then you vary your frequency, and then you get a resonance. On the other hand, when you are doing the field sweep experiment, you set up a certain specific frequency, and then you change your field, and you get a resonance with a certain field. So these are the way you can do your experiments, and these are the way one are doing. Now, let me give you another more schematic how it looks like when you are placing your sample inside the magnet. So this is basically the green part is, for example, a sample, and this is actually your magnet. And so that means the magnet is B0 is the magnetic field is applied perpendicular to the coil. And then your oscillatory, this time-dependent radio frequency field is actually perpendicular to the coil. So this is basically the geometry of your in general NMR experiments. And when you are talking about the in general the NMR experiment, so you know it is since the signal is very weak. In general, nuclear magnetization is very weak, and the same coil you are using for sending the signal and also the receiving the signal. So there is a kind of complicated, complex spectrometer you need. And in general, I will not go into the detail of this whole spectrometer concept. You can consult in some books and other things. But let me tell you only briefly that there are three parts of the spectrometer in general. So we call it as a transmitter, and the other part is actually the receiver. And then you have a computer where actually you can see all the transmission, receiver, and everything you can control from there. So there are many important parts of an NMR related experiments. So all the parts are very important. So like amplifier, duplexer, and then gate, splitter, and signal, oscilloscopes, everything's are important. Radio frequency generators and so and so. But there are two parts are actually essential. The first thing is actually every part is important. There is no question about it. One is actually the important is your magnet, because without the magnet, you cannot really do nuclear magnetic resonance experiments. Yeah. So therefore, I want to give you a little bit information about what kind of magnet in general nowadays people are using. So, nowadays, mostly people are interested in more higher the fields. So therefore, they try to get a superconducting. They wanted to have a superconducting magnet. And in the superconducting magnet, you have a kind of, for example, this is the cross-sectional view of a superconducting magnet. And in this cross-sectional view, you have your coil, which is immersed into the liquid helium. And then that provides a magnetic field in this parallel to this line. Yeah. And in the left corner, I have shown you one magnet which is actually cutted, how the inside of the magnet looks like. In the left corner bottom, this is the 1 gigahertz ion, the highest static magnetic field available now in this Bruker magnet. So this is really the great achievement from the Bruker now. So let's talk about general available magnetic field around the world now. What is possible to get? As I told you first, that this is the superconducting magnet, left side, Bruker magnet. This is the ion, it's called. This is the 1 gigahertz. So that means you can get a field of 23.5 Tesla. Yeah, so that means 1 gigahertz NMR is possible, and this is really high resolution NMR one can do. And but this is not the only field you can get. You can go beyond that. So that means you can go a field of 30 Tesla, but that 30 Tesla is actually your resistive magnet. So the resistive magnet means you really need a lot of energy to energize your magnet. Yeah. And then you also have a hybrid magnet, and this is actually available in Tallahassee, for example, in Florida, and the maximum field is actually 45 Tesla. And what is this hybrid magnet? The hybrid magnet is a combination of your resistive magnet and also the superconducting magnet. So that means by the combination of these two techniques, two magnets, you can go up to 45 Tesla. Yeah. And you can also go beyond that. That is actually the pulse field. And so there, so far, at least up to 62 Tesla, one have got the NMR signal up to 62 Tesla. At least in the Dresden, for example, Dresden-Rossendorf, the 62 Tesla, you can do NMR in pulse field. But in pulse field, performing NMR is rather challenging, because the NMR in general, you have a kind of long relaxation time. So, and the pulse field only persist or sustain for a millisecond, a very tiny amount of time. So, and in general, NMR is a time-consuming experiment. So therefore, more hiring the field, yeah, in particular, the pulse field experiments in NMR is really difficult. It's really challenging. But people still are trying to get more fields, like 90 Tesla or close to at least 100 Tesla. They are trying. They will try, and I hope that in sooner or later in Dresden itself, it will be possible to make. Okay. So another important factor of this NMR experiment is basically your magnet homogeneity, and this one should keep in mind that, for example, there are at least three ranges I disentangle as far as the magnet homogeneity is concerned. So I call it good homogeneity, and then I call it better homogeneity, and I call the best homogeneity. So the good homogeneity, I usually call it as 100 ppm over a 10 millimeter diameter spherical volume. So usually those who are doing the condensed matter physics, like broadline NMR, there it is okay. It will not hurt too much. You can survive with this. But if you want to do chemistry or very narrow line, yeah, then your magnet homogeneity has to be very good, like 1 parse per million over a large homogeneous volume, or the best homogeneity now, this 1 parse per billion, over a large homogeneous volume. Okay, so now I want to show you that how in general a lab looks like. For example, this is a small lab. We have different other labs also, but for a demonstration, I wanted to show you how in general a lab looks like. For example, this is a magnet, yeah, this is a 7 Tesla, 8 Tesla Oxford magnet, not so high homogeneity. And then this is this spectrometer console, and then you have a to operate your field, to control your field. This is your magnet power supply. So this spectrometer console is very small because for this particular spectrometer we have only varying the frequency from 4 to 125 megahertz. So therefore you don't need such a big spectrometer console, and then you only need a kind of radio frequency amplifier. In general, these are the schematics. These are the one representative lab what we have in our Dresden. Okay. Okay, so let's go to a little bit. I want to give you more information that about how to improve your NMR signal intensity, because I told you that that this nuclear magnetization is at least 10 to the power 6 times smaller than the electronic magnetization. Yeah, so if somebody tell you that, okay, I give you a sample, please measure NMR for me. Yeah. So then you have to think, okay, then first question you have to ask that, okay, how big the sample is? Because that to really get a usable NMR signal, yeah, you really need a 10 to the power 14 nuclear spins at least, yeah. So that means this is really a one shortcomings that if somebody tells, okay, I have a very tiny thin films, I have a very nano magnets, I want to do NMR on it, is it possible? Then you have to think about, first question you have to ask, how many nucleus you have in the system, yeah. Anyways, now the situation is getting improved, so people are getting more signal to noise ratio, and people are doing little bit different kinds of NMR to improve the situation. But still the restrictions are there, that how many nucleus are there to really get a reasonable or usable NMR signal. So this one has to think about it before you start or looking for or searching for the NMR signal. Yeah, for example, now in solid state physics, in what we do now, we can get NMR signal now 0.5 milligram sample also. Yeah, but if you really design a coil very suitably and your construction of the coil geometry has to be very good, then only you can get it. So that means there are a lot of restriction as far as sample dimensions or sample length is concerned. So now you have in general, the signal to noise of an NMR signal depends on your gamma to the power 5/2 and b to the power 3/2, here b is actually your field, external field, and then gamma is actually your gyromagnetic ratio. So that means that higher gyromagnetic ratio nuclear isotopes are easier to observe. So that means, you see, I told you that copper and you have proton and you have this phosphorus, all of them has a high gamma value. Yeah. And then you depends on your external magnetic field. Yeah. So that means more field you applied, you get a better signal. This is of course, this is the advantage. So that means you have to go really high field to really get a good NMR signal. But on the other hand, when you are applying the higher field, so that means your frequency is also higher. Yeah. So that means when you're hiring the frequency, means your noise generated by the electrons in the coil is also roughly proportional to the square root of the frequency. So that means higher the field means hiring the frequency, and hiring the frequency means your noise is also generating or getting higher. So therefore, this also reducing or also your signal to intensity. So therefore, but optimization, one has to do that kind of balance, is that more you apply the field, you get a better signal of your NMR. And then another NMR instrument, because these are the instrument I wanted to show you to give you a flavor what kind of instruments and what kind of things you need to really do this NMR. So for example, this is a NMR coil. Yeah, as I told you that how the coil is actually, you have to place your sample inside the coil. So this is actually one in the bottom I showed you, there is a coil, NMR coil with a sample. Yeah, and then you have 3 spectrometer and 3 capacitance. In general, you are using 2 capacitance, one for tuning the resonance condition and one for actually the matching. Matching means you have to have doing the impedance matching, so to get a perfect resonance condition. So this is actually the typical one bottom part of an NMR probe, and here you put the sample and your magnetic field actually the perpendicular to this coil, and this is signified, or this is indicated by this arrow. Okay, So now let's go to the information that what actually you can get the microscopic information by using NMR. Yeah. So when you were talking about the solid state physics or the condensed matter physics, what actually you get? Yeah. So in real material you have a nuclear moment, and that nuclear moment you apply the static external magnetic field to lifting the degeneracy of your ground state, yeah, or degeneracy of the nuclear energy levels. Now now your nucleus is actually surrounded by a lot of electrons, yeah, and that nucleus is actually interacting some kind of interaction to your surrounding electrons, and that is actually the hyperfine interaction, and that's very important. Those who are talking about the NMR in general. And by doing NMR, you can get two kinds of information. One is actually your static information, and that static information comes because of your NMR shift and line shift. And what does it mean by static information? Static information means this information doesn't contain any time dependency. So that means your line width or for your resonance position, this will not change as a function of time. And the second information you get, this is actually your dynamic information, or we call it spin relaxation. It may be a spin lattice relaxation or spin relaxation. So what does it mean? You have the abbreviation is actually something T1 and T2. So that means that is your electrons, which is your nucleus, and this nucleus is surrounded by a lot of electrons, and that electrons is also fluctuating. The fluctuation means it also produces a fluctuating field at the nuclear site, yeah, and that fluctuating field, yeah, essentially has a time dependency, and that time dependency is called the dynamic information, and that you can get when you are doing also the information. So that means by doing NMR, you are not only getting the static information, but yeah, hello, are you hearing?
You please proceed, sir.
Yeah, no problem.
Please proceed.
Yeah, because I heard a sound. Yeah, okay. So that means, so this is the real crucial information. Not only static information you get, but also you get a dynamic information, and that's somehow very very positive effects of, or very important important information by doing NMR. And similarly, these things also you get from the MUSR, but there you're more or less restricted with your time window. If time permits, I'll also explain to you the whole techniques of the MUSR, at least some essence of the MUSR. Anyways, so I told you that how to get your NMR spectrum. This is but there I just try to represent with the spin half system to simplify the matter. So this is basically the line shape usually you get in NMR experiments. You apply the static field. For example, you have a spin half nucleus, and then you have a G-man interaction, and then in G-man interactions, and then you have a resonance condition, and then you get a field sweep NMR spectrum. You get a kind of H0 field. You get a resonance position. Yeah, you get a resonance line. Now, what you are doing, as I told you, that you have a kind of hyperfine interactions, yeah? And then electron produces some kind of additional field at the nuclear site, in addition to the external field, yeah? Now, as soon as you do it, what you get, your resonance position, so that means your Zeeman Hamiltonian becoming not only this H0, which is actually the static external field, but also you have an additional field, yeah? This is the delta H. And that delta H gives you a shift of your line. So that means originally your line was actually at the H0 position, but now your line is actually placed at H resonance position, yeah? And that is actually it is called a kind of shift, yeah? And in condensed matter physics, those who are doing in the metal, that is called the night shift, yeah? Because that was discovered by night. So that means but this is called night shift. So that means that gives you the local susceptibility of the system you are measuring, yeah? Now, people may ask, okay, this is also information that what you are getting by some kind of hyperfine interactions, and you're getting some kind of shift, and you get information. But what is the advantage of it? The advantage of this is that it gives you a very local and a microscopic information. This is the real information. So that means if your system possesses some kind of, or the lot of impurities, and then you make a bulk susceptibility or the bulk magnetization, you'll get a bulk effect, you'll get an average effect. But if you make a local probe technique, local probe like NMR or MEOSAR, then you get a locally what is your magnetization, locally what is your susceptibility, because this is actually your night shift is proportional to your local susceptibility. That's the microscopic information you can get, and this is the unambiguously you can determine what is the susceptibility, local susceptibility of your system. So that's really a very crucial information for that. Now let's go to our so far I was talking about the static part. Now let's talk about little bit about the dynamic part. Yeah, that means the spin lattice relaxation rate. So I told you in thermal equilibrium, in the left cartoon, you can see how the states are distributed. So in the thermal equilibrium, you see your ground state is much more populated. Yeah. Now what you do, you make a kind of excitation. So that means you get some kind of radio frequency, time-dependent radio frequency things. So that means your thermal equilibrium state is actually destabilized. And then you become a kind of excited state. So for example, the excited state means you have the ground state and the excited state. Now, for example, you have a kind of equal population. Yeah. So that means this is an excited state. But all the state doesn't like this situation because this is the unequilibrium condition. Yeah. So therefore, what they're doing now, they try to interact with their surroundings. For example, in solid state physics, we call it lattice. So you have a nucleus, and rest of the things apart from the nucleus is basically lattice. So now they try to interact with your lattice, and this is a kind of exchange of energy. So as they do the exchange of energy, what they do, and that means there is a kind of time you need. This is for example, the spin lattice relaxation time T1, and then your system comes back to your thermal equilibrium, the right side of the picture. So that tells you, so that means you have to measure somehow these T1 values to really know how your system comes back from your excited states to the thermal equilibrium state again. And that gives you the information about the spin lattice relaxation time or spin lattice relaxation rate. Now some may ask, what is the importance of these things? The important thing is that T1 basically varies how your nucleus interacting with your surroundings. Yeah. So that means depending on the fluctuations or depending on the dynamics of the electrons, those who are actually surrounded this nucleus, and that information will be reflected onto your spin lattice relaxation rate or the spin lattice relaxation time. And by measuring these things, then you can get the information about the dynamic nature of the electrons. And so that means you can get a dynamic information of the whole solids, what you're measuring. So there actually, it is a really important thing and really information. But I have to admit that all the information you get very low energy fluctuations, not very high energy dynamics you cannot get. I already told you the information you can get by using NMR and MEOSAR is the fraction of microelectron volt. And neutron scattering, for example, you can get the information in the energy scales of milli-electron volt. That one has to keep in mind. So that means the low energy spin dynamics you can get by using this kind of relaxation time. Okay, so there are several ways you can measure. So inversion recovery, saturation recovery, I will not go into the detail, but at least I would like to mention that for inversion recovery, this is mainly used for narrow line, and for the saturation recovery, this is mainly used for the broad line. Anyways, in general, the equation we try to use for the spin lattice relaxation rate, this is one of it for the correlated electron system. In particular, the correlated electron systems means in a material where all the electrons of your system are strongly coupled, yeah, not really independent. So that means one electron's information is actually coupled to the another electron. So that's the somehow the way of understanding the correlated electron systems. So now if you see a correlated electron systems and you are talking about the spin lattice relaxation rate, this is given in general proportional is equal to the imaginary part of your dynamic susceptibility and then transverse components of the magnetic hyperfine field. So that means by this T1, basically you get an information about the imaginary part of the dynamic susceptibility and also the magnetic hyperfine coupling, but only the transverse component. Now, so that's the general equation I have told you. Now let's talk about if you really get a metal. For example, you take aluminum. If you take a copper, then these are the simple metal, right? And the simple metal or gold. Now, if somebody gives you a metal and tells you, okay, Rajib, please measure the spin lattice relaxation rate, and what should be your rate? Because, you know, when you are doing the solid state physics on any research, first thing we have to know, rather than going to the complicated things, so most of us first try to ask some basic question, very fundamental question. If you understand that basic and the fundamental question, then only you can think about big theories and big question. First, you have to understand the very fundamental issues. So that means, so for example, in a simple metal, if somebody asks you, okay, what would be the relaxation rate? Then you have to tell, okay, my relaxation rate would be proportional to temperature. 1/T1 proportional to temperature. And this actually follows our equation. It is called Korringa relation. So for example, I exemplified here Ka square, which is actually the night shift of the metal. The night shift is also for the metallic system. And then you have a spin lattice relaxation time, and then temperature, which is actually the constant value. Yeah. Now somebody asks, okay, that's the constant value. This is great. Yeah, that's the information one has to have. Now somebody is telling, okay, I have a metal, but in my metal, this is a conventional Fermi liquid in a sense, but there is no correlation in my electrons. But now somebody tell you, oh, let's introduce little bit correlation. Let's introduce little bit correlation, like my electrons are now, the ferromagnetic correlations are present, or I have an antiferromagnetic correlations are present. But how do you determine these things? Yeah, this is very tricky, very difficult to determine. There actually, this Korringa relation will actually help you very nicely, because then, so here actually you can define your K square T1T equals to alpha into S0. And here S0, I told you, this is basically your Korringa constant. And then alpha is actually your strength of possible correlation. Yeah. When alpha greater than 1, then you can tell, okay, in my system, the ferromagnetic correlations are present. If your alpha is less than 1, then you can tell, okay, I have antiferromagnetic correlations is present. So this way, even if you have a metallic system and some correlations are present, and then you can provide the information by doing this kind of Korringa plots, or the Korringa relation, or Korringa constant value. Okay, so far so good. I try to give you some flavor. So how the basic developments of the NMR took place, and then I talk about what are the what to locate NMR, and then I talk about what are the applications of NMR, and then I talk about some general basic principles of NMR, and then I talk about what are the experimental equipments you need to understand NMR, or to perform NMR, and then I try to explain what is night shift, that means NMR shift, and then I also told about spin lattice relaxation rate, or spin lattice relaxation time, and so far so good. Yeah. And then I also talked about this the Korringa constants and so on. So these are the very fundamental and basic information. Now I want to tell you, then when you are talking about the condensed matters physics, yeah, what are the scopes of NMR? Yeah. So that, you know, the condensed matter physics and general solid state physics, in particular the correlated electron systems, is a very wide field. Yeah, many research are going on around the world. Outstanding physicists, chemists are involved in this particular field. Yeah, and so there are outstanding discoveries are also coming up. So for example, when you are talking about magnetism, by using NMR, you can get the information about what kind of magnetic state, internal field, magnetic structure you can get. In the frustrated magnetic system, you can get about your dynamics, about your local susceptibility you can get. You can do many quantum magnetism, you can get very quantum information. Yeah. In heavy fermion system, where fermions are actually much heavier than usual fermions, there also the NMR was extensively used. Yeah. And one of the very solid application of NMR over the years, yeah, is actually the superconductivity. Yeah, the both conventional and unconventional. And then modern days also, now people are trying to get a lot of information about the topological aspects of matter, in particular the wild semi-matter. So in condensed matter physics in general, we have a wide applicability of this nuclear magnetic technique, nuclear magnetic resonance technique, equally for muon spin rotation technique. So I cannot cover all the topic, but I want to give to the students and the researchers a little bit flavor of one example in superconductivity, what you can learn by using NMR. I hope this will be helpful for some of us to get a flavor how you actually use this NMR technique to understand the superconducting properties of superconductivity, which is an outstanding phenomenon. I'll slowly explain to you. Okay, so with the specific example, I'll give you iron-based superconductors. Let's see how much time I can have on these things. Okay, so first let me briefly explain you why superconductivity. Yeah, so you know that superconductivity is an extraordinary quantum phenomena. Yeah, so if you take a normal metal, hello. Oh, sorry. Okay. If you take a normal metal, so your resistance, as you're lowering the temperature, goes down. Yeah. But so in Kamerlingh Onnes from Heike Kamerlingh Onnes, actually in 1911, he was actually what he was doing. He was basically measuring many metal and trying to see what is the resistivity or the resistance of this metal happening as he is lowering the temperature. Because he was the gentleman first cooled down the liquid helium 4.2 Kelvin. Yeah. So, and what he observed in 1911 that, as he is decreasing the temperature, the mercury, immediately the resistance goes to zero or close to zero, very low resistance, below 4.2 Kelvin approximately. And he was surprised by this phenomena because nobody has observed such a phenomena until that time in 1911. The discovery was outstanding. And in 1913, Kamerlingh Onnes actually got the Nobel Prize for his work on the low temperature physics in particular, because for his liquefations and so and so. But at that time, and in 1912, nobody knew what is the importance of this discovery, because nobody knew what is superconductor at that time. Yeah, so therefore it was very hard to understand what would be the future, what would be the fate of this discovery later on. Anyways, in 1913, Kamerlingh Onnes got the Nobel Prize for his contribution to the low temperature physics in general. Now we know this is a tremendous application of superconductor, and it is a tremendous physics, the quantum phenomena and the physics problem, or the both chemistry and the physics. This is the outstanding research one can do on this particular topic. So far, now we have in applications of superconductors, like you have in particle accelerators, generators, in magnet, and B field detection in squid. There are many applications that are coming. So I hope that if you can get a room temperature superconductivity, probably everything will be revolutionized. So whole dimension of life probably change. That we don't know. So that is the future story. So we cannot predict future. Anyways, so why superconductivity and how this is developed? So as I told you, 1911, you have a discovery of superconducting phenomena, and 1979, that was the first discovery of heavy fermion system, the heavy fermion superconductor, and that was in particularly the cerium copper to silicon 2, and that was the first unconventional superconductor where the superconductivity has been obtained in the presence of magnetism. And before that, 1979, people used to think that superconductivity and magnetism basically a kind of antagonistic. They don't like each other. But nevertheless, it was shown that, okay, even in the presence of magnetism, the superconductivity can be obtained, and which is found also in high TC cuprates, 1986. People got the Nobel Prize for this, for the discovery of this experimental physics. But so far, there is no real theory available that can tell you or justify that your superconductivity, the high TC Cupret superconductivity. And more recently, in 2006, we have a Another sets of superconductor games. This is the iron pnictide superconductors, and this is also unconventional nature, and this is also very interesting fields of things of this pnictide. So I'll give you briefly a little bit about this iron pnictide superconductors in general. So why superconductors are important? I told you that it is a striking physical phenomena, right? It's a wonderful phenomena, yeah, and it's a manifestation of quantum effect. So that means this is the real. If you really have to understand the superconductivity, you have to understand the quantum effect. Otherwise, you cannot do it. The total disappearance of resistivity. Yeah, your resistance is completely gone. Imagine a situation: you put a copper, you put a current there, and it's heated up. You place a lot of energy, you lose a lot of energy there, radiation loss, and so and so. But in a superconductor, you place a current. If your thought experiments you do, the current would be infinite time. There is no loss. Yeah, and then you have exclusion of flux. And then you have a flux quantization in microscopic cylinders, and then more detail, more information like interference effects between junctions, so on, so you can get. But as an NMR, you cannot probably directly give all the information. Yeah, but NMR has the capability to tell you some important aspects of superconductor, like you can tell, whether this is a unconventional superconductor or this is a conventional superconductor. That you can tell. You can tell the information. What is the night shift? That means the local susceptibility of this superconductor. You can tell about what is the wave symmetry of the superconducting ground state. So these are the very crucial information those who are working in the field of superconductivity, and you can get by using these things. So I think I'll not. So what I want to tell you, just briefly, quickly showing you. For example, if you take a 27 aluminum metal, yeah, this is a very nice pure metal, and you make a night shift of the metal as a function of temperature. You see, below a certain temperature, your susceptibility or your local susceptibility, this night shift is actually going down very sharply. So that tells you that how your singlet state at the microscopic level is Cooper pairing singlet state is forming. That you can get. And additional interesting information, what you get, there is a kind of peak as you are entering in the spin lattice relaxation rate, as you are entering in the superconducting state. Yeah. Why this is happening? It's happening because you're opening up a gap in the superconducting state. It may be isotropic gap, it may be an isotropic gap, depending on the superconducting wave symmetry. So there you can get different types of gap. But that you can get from this information. So that means that gives you a preliminary idea what kind of gap in your system possesses. Yeah. So that's the crucial things. So anyways, so to two classical signatures of in general BCS superconductors by NMR one can get. BCS means Bard and Cooper Schrieffer superconductors one can get. The first one is that exponential decay below TC. So that gives you, that means this is you have a very isotropic gap in your system. And then it tells you that Hebel-Schlichter coherence peak. Okay, so now if you give me a superconductor, now first, if you really want to understand microscopically whether this is a BCS superconductor or not, then I will tell, okay, I will measure NMR and I will tell you, okay, these are the classical signatures of BCS superconductors, and I can tell you this is a BCS superconductor. If you go beyond that, then I will tell, okay, there might be some kind of unusual gap symmetry is present in this particular system. So therefore, that is the starting point for your really making a kind of go-ahead situation with this NMR. So I just want to tell you, for example, how the relaxation rate looks like. For example, one conventional superconductor to an unconventional superconductor. Like you see in the left plot, this is the spin lattice relaxation rate as a function of temperature. You see, and this is actually this is actually the data for spin lattice relaxation rate, and so that tells you that if you take a conventional superconductor, that means the BCS superconductor, one should really see a Hebel-Schlichter coherence peak there. Yeah, and that is somehow missing here. So you only get some kind of opening of the gap, and it's slowly increasing the relaxation time. That means 1/T1 is decreasing. Now, if you compare with other superconductor like magnesium diboride, aluminum, which is a BCS superconductor, cerium, cobalt, indium 5, and then plutonium, cobalt, gallium 5, you can see this is really the Hebel-Schlichter coherence peak is missing there, and then you have an unusual gap symmetry opening as you are entering in the superconducting state. Anyways, so that was the information you can get. Now let me tell you, so how much time do I have? Hello?
Hello, sir.
How much time do I have?
You can take 20 more minutes, 15 to 20 minutes.
Okay, 20
Yeah.
minutes. Okay, thank you.
Yeah.
Yeah. Okay, so now I want to give you some very recent example, because so the idea of my talk was that to give you the flavor how this NMR technique develops slowly, and then give you some brief ideas what you can do with this NMR. Now I'm to give you more very advanced state of research, what actually around the world people are doing in the framework of general iron-based pnictide superconductor. I cannot tell everything because the limitation of time, but I want to give you a flavor that around the world now, what is the state of the art situation, for example, your iron-based pnictide superconductors, and what are the problems and what are the questions are there one can really want to ask and want to know. For example, here I told you that iron-based based superconductor, which has been discovered in around after 2006, and then in 2008, actually this lanthanum 1111, there was a superconductivity appeared up to 26 Kelvin. Yeah. So why these iron-based pnictide superconductors are so hot and so important? That was important because it has a very wide ranges of material you can get. Yeah, one can get 1111 like iron selenium. You can get 111, so that means lithium, iron, selenium, and then 122 structure, and then 1111 structure, and more. So more complicated structure. In all of them classes of materials, what you have, that means the different classes of iron arsenic layers, you have a iron square lattice as a common feature, and then you have a different buffer layers. Okay, so if you really make a different types of doping or introducing some kind of disorder, you get a kind of real superconductivity on the system. So that's really very very robust. Yeah. And what you tell is usually the word, the iron is still hot. You know, iron is discovered, I don't know, maybe 4,000 years ago, but you see the still iron producing such a fascinating properties of the matter in particular in your iron-based superconductor. Yeah. Why this is so interesting, not only from the point of view of the superconductivity, but in general, when you are talking about the magnetism and the superconductivity, interesting physics is concerned, then it's also interesting. Why? Because you have a parent compounds of these iron-based superconductors are actually the semi-metal. It's not a metal, it's not insulator, but it's a semi-metal. Yeah, but you have a very complicated Fermi surface. Yeah, you have a whole Fermi pocket surface at gamma point, and then you have a electron Fermi surface at M point, and you have a crystal field splitting smaller than bandwidth, and all 5 3D bands. You know, when you are talking about the iron electrons, then you have a 5 3D bands, and all 3D bands are actually crossing these Fermi energy levels. And so that means these iron pnictides, you have a many degrees of freedom. Yeah, so many degrees of freedom, and many degrees of freedom means you have very rich physics. Yeah, so that means you can really do a very a lot of interesting physics you can do. Of course, you can get an application and technological things. This is also important, but additional important things to know, to understand the physics, to understand the nature, to improve your knowledge. Yeah, so that you can do also by doing this kind of physics. So that's the reason sometimes it is not all the time it is important that all the time you have to do the technological implications or application thing. This is important, but it's also important to have your knowledge, the improvement of your knowledge. So that's the reason I think the many degrees of freedom and very rich physics also fascinates a lot of physicists and chemists around the world on this system. So in this whole branch of iron-based pnictide superconductors, the parent compounds, this is barium iron to arsenic 2, is one of the best studied parent compound. Why? The reason are the following. if you take a parent compound barium iron 2 arsenic 2, this poses a spin density of antiferromagnetic ordering at 135 Kelvin. In addition to that, exactly the same temperature in the parent compound 135 Kelvin, there is a tetragonal to the orthorhombic phase transition. That is the structural phase transition. Okay, that's fine. So you have a magnetic phase transition and you have a structural phase transition. So that means you have a symmetry is changing. Okay. Now you dope the system some kind of electron doping or hole doping. You get a range where the superconductivity emerges in this system. That is also fine. But additional interesting things happens here. What is happening, there is another phase, what is called the nematic phase. Now, what is nematic phase? Nematic phase means your translational symmetry is broken, but your time reversal symmetry is preserved. So that's really interesting, because in your system, as you are increasing the doping, what happens in a certain ranges of the doping, you have a kind of the nematic fluctuations of the nematic order takes place. And that was really important to know, because many people thought that the superconductivity in this iron pnictides emerges on the state of also from the nematic phase. So therefore, one has to understand the nematic state of the matter of the system. Then only you can understand where from the superconductivity emerges. Yeah, so that's the reason it was important for us to know to understand the nematic state of this system. So what happens? Initially, the Fisher in 2012, they measured a kind of nematic response of the system. How do you do the nematic response? You basically make a kind of strain tuning into a system, and then you make the resistivity, and you try to see changes of the resistivity as you change your electric displacement. And what they have found as a function of temperature, this is the plot of the nematic response. There is a divergent nematic response exactly at the structural transition, and that actually fascinates them. So therefore, they are thinking that nematic fluctuation is really, really crucial in this barium iron 2 arsenic 2 system. So our target to really understand what these nematic fluctuations look and what we can get from the NMR. Yeah. So initially, when we start the problem, at that time, what is known for us? We knew that in this particular system, there is a present of dynamics, or the spin dynamics, or the spin fluctuations, and that are anisotropic in space. And this is the direct consequences of the existence of the spin-orbit coupling. So these people you know when you started the problem. That was, I think, 2017 or 17. And what is unknown, at least we didn't know, if there is an interplay between your spin fluctuations in spins and the real space. If there is so, how to know it? Yeah? And therefore, we thought, okay, let's do a kind of special nuclear magnetic resonance experiments on a different field direction in uniaxially strained samples. So as I told you, that one of the things we have to do, you have to varying your environment, and that's the thing we have done. So for that, we have developed our, together with the UC Davis, California, we have developed a kind of probe and this positive and strain. These are the experimental details. If you really want to learn all the things, you can follow my papers and so and so. So these I will not tell. What I want to tell you just quickly is that this is basically my sample, or our sample. We have located here, and this is our coil, and this is actually we want to apply the strain in this direction, and the other geometry, you can see the 1 millimeter to 1.5 millimeter of sample, and then you have a coil, and then we can apply the strain and straits to the system. So with that, what we have found, the first experimental observation, that as you measure first the static susceptibility, that means the night shift. We see that as you lower the temperature as a function of displacement, this is the displacement, and this is the night shift, or the NMR shift. As a function of displacement, the shift doesn't change at all. Yeah. Okay, that was a little bit surprising for us, because the constant night shift means the strains suggest that the local susceptibility weakly couples to the strain. So that means you strain the sample. So that means you change the lattice constant somehow of your system, and this somehow not really changing your local susceptibility. But when you do the measurements of your electric field gradient, that I have not mentioned, but the electric field gradient, another parameter one can do, that gives you the information about your local structure of the system. You see, the electric field gradient is is changing linearly as a function of strain. And that's really important information. And that's a linear relationship with strain suggests that both positive and negative strains are achieved without bending of the crystal. And that is important because when you apply an uniaxial strain, you always want to know that by applying my strain, whether this system is somehow making some crack or some kind of broken in somewhere. If you have a linear relation, so that you can tell, okay, I have no really bending of the crystal, so that is uniformly or homogeneously reacting with my uniaxial strain, and that's really an important information. Now, if you really want to do some NMR experiment, or if you want to do some strain experiments in some other system, and you want to know by applying what kind of strain, what is there any change of your lattice constant, change of your bending of the crystals, or some kind of problem in the crystal, that you can identify by doing NMR. Of course, this the job is a little bit harder, but at least you have the possibility to do these things. And then I will not talk about the other part, this because the limitation of this time. So then we have done the spin lattice relaxation rate in two different directions, and that's really crucial and very important information. So the upper plot is showed when I apply my applied field in parallel to z direction and measure T1T, and then you see only tiny dependence with respect to strain. Yeah, but when you apply the other perpendicular direction, you see you have as the higher temperature, this is the relaxation rate is more or less flat, but as you're lowering the temperature, your relaxation rate is dramatically changing. In 137 Kelvin, it really shoots up. So what does it mean? This tells that you have a very strong anisotropic spin dynamics into the system. That more tells that both positive and the negative strain increases as a nonlinear function. And this also tells that this is a manifestation of the spin anisotropy induced by the nematic order. So all the very crucial information you can get out of an NMR, and you can do a lot of calculation out of it, and then you can get what kind of polarization into a system, and so and so. So far so good. With this, I would like to give to the concluding part of this section, that NMR essentially gives you the information about, and this is actually the first NMR experiment or any NMR experiments under uniaxial strain we have done in California, and now we are trying to implementing these things in Dresden also, and we will do it not only for nuclear magnetic resonance but also for muon spin rotation. This we have already developed in Dresden, and slowly things will come up, and many interesting physics you can do for sure. And then striking difference, as I told you, then relaxation rate between two crystallographic direction. So that indicates you have an anisotropic spin dynamics. And NMR extracted nematic susceptibility also agree with other experiments. In addition, NMR explores the entanglement of spin and real space anisotropy. And many correlated system in future worth to visit: any low-dimensional system, frustrated magnetic system, systems with delicate Fermi surface topology. Wherever you have a Fermi surface and it is a kind of delicate, then you can apply your strain, and you can get more important and crucial information. So now that's both NMR is good, because NMR you can use 1 millimeter over 1.5 millimeter sample. But I have not time. I don't have the time to talk about muon on this system. Muon is also possible to do on uniaxial strain, but there you need a geometry of the sample of something 5 millimeter or 4 millimeter because of the muon experimental restriction conditions. I hope near future, if I will have some other opportunity, I'll talk about the muon. But today, I think I don't have the time to really talk all these things. So thanks for your attention. And I'm extremely sorry that initial inconveniences you people have suffered. I'm very sorry. This have never happened to me. Such unprofessional presentation. I'm extremely sorry for that.